Imagine a roller coaster climbing a hill, dropping into a valley and rising again. At the top, it may be moving slowly, but it has height. At the bottom, it has lost height, but it has gained speed. The motion looks dramatic, but the energy bookkeeping can be surprisingly simple. In this video, we will focus on a powerful idea. When friction, air resistance, and other energy removing forces are negligible, mechanical energy is conserved. That means energy can change from between gravitational potential energy and kinetic energy, but the total amount remains the same. So let's start learn about conservation of mechanical energy. The principle of conservation of mechanical energy says that the total mechanical energy of an object remains constant if the net work done by external non-conservative forces is zero. Let us unpack that carefully. Mechanical energy is the sum of kinetic energy and potential energy. Kinetic energy is energy due to motion. Gravitational potential energy is energy associated with height. So, when we say mechanical energy is conserved, we mean the total of kinetic energy plus potential energy at the beginning equals the total of kinetic energy plus the potential energy at the end. This does not mean kinetic energy must stay constant. It also does not mean potential energy must stay constant. Each one can change. For example, as an object falls, gravitational potential energy decreases while kinetic energy increases. The key is that the total mechanical energy stays the same as long as we ignore non-conservative effects such as friction, air resistance, or an engine doing extra work on the object. So when the energy is conserved, total mechanical energy at the beginning is equals to total mechanical energy at the end. This slide shows how the conservation statement comes from the work energy relationship. In a more general situation, non conservative work changes the mechanical energy of the object. In words, non conservative work equals the change in kinetic energy plus the change in potential energy. For example, friction is a non conservative force. If a box slides across a rough floor, friction removes mechanical energy and turns some of it into thermal energy. In that case, mechanical energy is not conserved. But if the net non conservative work is zero, then there is no loss or gain of mechanical energy from those external effects. So the relationship simplifies to the most useful form for this lesson. Initial kinetic energy plus initial potential energy equals final kinetic energy plus final potential energy. Now let us apply the conservation of mechanical energy to a real example. A motorcyclist drives horizontally off a cliff with an initial speed of 38 meters per second. The starting height is 70 meters and the final landing height is 35 meters. We are asked to find the speed with which the motorcycle strikes the ground on the other side. A very common first thought is to solve this as a projectile motion problem. That would work, but it is not the most efficient method if we only need the final speed. Energy gives us a shortcut because gravity is a conservative force and we are ignoring air resistance. That means the loss in gravitational potential energy becomes a gain in kinetic energy. Notice something important. The motorcyclist leaves the cliff horizontally. That tells us the initial velocity has no vertical component. But It does have a horizontal speed of 38 meters per second. Energy does not require us to separately track horizontal and vertical components. It only needs the total speed and the height at the initial and final positions. So our plan is simple. Compare the mechanical energy at the launch point with the mechanical energy at the landing point. Here we set the final mechanical energy E final equals to initial mechanical energy. This is the same idea as saying energy at the start equals energy at the end. At the top of the cliff, the motorcyclist has gravitational potential energy because of the starting height, and kinetic energy because the motorcycle is already moving at 38 meters per second. So we can write E naught is equals mgh naught plus half mv naught square. Final total energy will be mgh final plus half mv final square. And we can use this in our equation. We get mgh final plus half mv final square equals mgh naught plus half mv naught square. And here we have m in all the terms, so we can divide everything by m, so m cancels out. And we can multiply both sides by 2, so we get 2GHF plus V final square equals 2GH naught plus V initial square. And we can send this part to the right hand side of the equation, so we get V final squared is equals to 2GH naught minus 2GHF plus V naught square. From here we can factor out 2G, and then from here we get the final velocity is the square root of 2G h naught minus h final plus V naught square. Now we can substitute the values. So 2 times 9.8 meters per second square times h naught is 70 meters minus h final is 35 meters and plus initial velocity was 38 meters per second, and that is squared. And after simplifying this, we get 46.2 meters per second. Now this result makes physical sense. The final speed is larger than the initial 38 meters per second because the motorcyclist ends at a lower height. The missing gravitational potential energy has become additional kinetic energy. Also notice that we found the impact speed without calculating the time of flight and without using the horizontal distance across the canyon. That is one reason energy methods are so useful. When the question asks for speed and non-conservative force are ignored, energy can often solve the problem more directly. The final topic in this part is power. Power tells us the rate at which work is done or the rate at which energy is transferred. Two people can do the same amount of work, but if one person does it in less time, that person produces more power. For example, walking upstairs and running upstairs may require about the same gain in gravitational potential energy if the height is the same. But running up the stairs takes less time, so the power output is greater. The average power is the work done divided by the time required to do the work. The SI unit of power is the watt. 1 watt means 1 joule of work or energy transferred per second. The slide also gives the conversion between horsepower and watts. 1 horsepower is 746 watts. This unit is often used for engines and motors. For motion at constant speed in the same direction as the applied force, power can also be described as force times velocity. In words, if a force is doing work while an object moves, the rate of doing that work depends on both how large the force is and how fast the object is moving. So, work tells us how much energy is transferred, while power tells us how quickly that transfer happens.